So Graeme tells me he's got lots of things to get through, so we'll just let him get on with it and find about machines that go bing. Let's give him a good welcome.
Thank you. Technology, it's beyond me. This talk I will upload later today. It's packed full of pictures which I've not bothered to scale down, so it's about 18, 19 megabytes at the moment. And I promised that I would not upload or download vast amounts of stuff from here, so I will, when I get back to the hotel, I'll put it up on my Bitbucket account. There's about 65, 70 slides, so we are going to go pretty quickly in the next 40 minutes. I want to cover just a general overview of what real-world control is. And then let's talk about how Python can fit into that, because most people don't associate Python with real-world control. Talk about some of the gotchas that will happen along the way, especially with everyone's favourite of concurrency and performance. They're usually the two things that trip people up. I'll wrap up with just a few bits of advice, some tips, some tricks and traps that have caught me over the years, and then talk about where this could go in the future. So buckle up and let's go for the ride. What is real-world control? If you're not familiar with terms like embedded system and real-time programming and that, basically an embedded system is a single-purpose computer. It could be a mobile phone, it could be the smart little microprocessor in the back of your microwave oven. It could be the pacemaker that you've got ticking away in your heart at the moment. It usually has real-time constraints, especially if it's a pacemaker. You want that thing to just work really reliably. And that's where real-time systems tie in, because the events have to occur within specific time constraints. It may have to happen precisely every n number of microseconds. It may have a window within, as long as it happens within that window, you're okay, but it can't exceed that window or can't go under that window. And failure to do so can be catastrophic. Your pacemaker, for example, the shutdown sequence for a nuclear power plant. And it's actually incredibly difficult to program complex real-time systems correctly and guarantee that they will work. You know, if you're designing a nuclear missile, for example, or a rocket to take people into space, you don't have a lot of chances to get it right before it actually takes off. And there's a whole range of different tricks that can catch you here, and we'll cover some of those along the way. So examples, if you've been in an aeroplane recently, it's all fly-by-wire. The days of old hydraulic systems are gone, it's all controlled with digital signals. Factories, car engines, the DSPs, digital signal processing, is all real-time. I mentioned pacemakers, a whole range of robotics, biomedical instruments, which is the area I specialise in. The machines that, when you give a blood sample, you take it away, it disappears somewhere, it goes into a machine that processes hundreds of those samples every hour. Do you have HIV, hepatitis? Are you pregnant? Are you showing markers of hypothyroidism? All those sorts of sickness markers or disease markers that you want to know about. And then simple things like networking products. Have a look at the technology that goes into your standard Cisco router these days and the performance requirements for that. It's pretty impressive. And home automation, which you can buy systems or you can roll your own. We'll touch on that along the way. So we're going to cover how Python overlaps with real programming, how Python overlaps with hardware, and talk about the sweet spot in between. The basics of measurement and control. Measurement can be digital, on, off, Boolean, or analog, where it's actually real-world values, voltages and that. Control is similar. Are you switching something on or off? Are you actually putting out a frequency or a voltage? That's the basics of it. So most of these things would be familiar to you. Sensors that can measure frequency, can measure a gas concentration, like how much alcohol is in the air that you're breathing out for the officer, light, temperature, humidity and the like. There's things like that GPS chip, the Infineon GPS chip, which is just tiny. It's a couple of millimetres high and wide. Barcode readers, RFID tags that are used to track where you're going. And lots of outputs, which you'll be familiar with. LCDs, like most of you are sitting in front of at the moment as you tap away. LEDs, ultrasonics, which are both input and output, buzzers and the like. And then it starts to get a bit more fun with things like relays and solenoids and the various types of motors that you can assemble up into building blocks to actually move things around. And this is just a stepper off one of the robots at work. It's got a belt, a drive belt that it's hooked to. And what that means is you can keep the stepper motor in one position and have that belt driving an axis somewhere else that allows it to whiz up and down a particular axis. You put enough of those together and you start to get X movement, Y-axis movement, Z-axis movement, and you can start to do some very nifty things in 3D space. And so that's a typical SCARA robot there, pick and place. So they're used for things like, in factories, bolt and arc welder on the end, as you do, and then you can automate the arc welding of cars and other large bits of metal. A bank of pumps, a bank of syringe pumps, each of those has a stepper motor or some other similar sort of motor behind it that allows you to drive out very precise micro-fluidic volumes of fluid. And an XYZ robot. The two probes allow you to put connections into pumps, and so you can whiz around and suck and squirt very, very small amounts of fluid. And the ability to do that very quickly is the backbone of combinatorial chemistry, a lot of genomics these days, being able to just program vast numbers of small wells to be mixed around in all sorts of combinations. And we're talking for, say, a metre axis, you can travel that in a second very precisely. So it's quite impressive. In terms of comms, name and acronym, it's bound to be there. So all the typical usual suspects like serial and USB, but there's also a lot of other dedicated ones that are really designed for real-world control. Things like CAN. If you drive a high-end European car, it's probably wired with just a couple of CAN bus wires that run around it as a distributed network. And then wireless protocols like, well, 802.11, A, B, G, N, Zigbee, Bluetooth, etc. Right. So I've just covered a few years of electronics for you. Now let's talk about how Python interacts with real-world control. In the old days, back when I was a young boy, computers were A, expensive, fast computers were incredibly expensive, and if you wanted a fast computer, it wasn't going to be small. RAM was incredibly expensive. I remember saving up for something like a 16K expansion module for my first computer, and it cost me an arm and a leg. What that meant for anything that was embedded was that if you wanted to commercialise a product, have it small and that, you were talking highly optimised coding and as close to the metal as you could possibly get so that you could get every single bit of performance out of that microprocessor. You never ever found scripting languages involved, certainly not for very real-time programming work. And then our friend Moore came along and he saved the day. Well, perhaps he didn't save the day, perhaps he just observed that the day was being saved. But if you look back at 1971, transistors were around the 2000 mark in an IC, integrated circuit. If we run up to today and you look at things like your quad cores, your 8-core, 10-core CPUs, we're talking 2,700 million transistors. And that sort of curve, that exponential growth, has allowed us to start moving away from the metal and not having to be so incredibly optimised to get good performance out of embedded work. So the benefits of Python, a lot of this I don't need to rehash, but from an embedded perspective, it's really nice for rapid prototyping while electronics engineers and mechanical engineers are developing the hardware. You can bring in Python on top of it and be very rapidly prototyping and experimenting without having to go through the usual compile, download, debug cycles. Lots of libraries, really easy to teach to scientists and engineers, and Ed's touched on that in another session today. I'm not going to labour the point. The drawbacks. Yes, there are drawbacks. It's slower than assembler. It's typically slower than C and C++. Slower to possibly perform, but not slower to write and actually get to a working prototype. It's often not suited to hard real-time, certainly not when you're down into the microseconds, the nanoseconds, the femtoseconds. There's lots of layers between the actual electronics and the Python interpreter. Limited static analysis tools means that you sometimes don't get the level of checking that you want before you ship your pacemaker out. And the garbage collection can get in the way, as it does with any garbage collected system. You can't guarantee that the system is going to perform really uniformly on a discrete time basis. There are ways around that, but won't touch on that now. Typically, it's not optimised for embedded targets, but people have done some work. There's what's called Pymite, or Python on a chip, which is targeted at things like embed boards and Arduino boards, this sort of size. So running in kilobytes of RAM, it's pretty impressive. And the other drawback of Python is if you want to write code for doing work in laboratories and that, at the moment you're having to roll it yourself. There's nothing like Labview out there for Python. But it's not all bad news, and that's what this session's about. It's actually talking about what we can do to understand the problem, what we can do to understand how to work around some of the constraints, work with the hardware rather than against it, and some of the opportunities. The two main ways of using Python in the real world is, one, just run it on your stock standard PC as you would normally, but push all of the real-time control down into dedicated hardware that sits in some form of interface board. There's a really wide range of small, cheap, powerful boards out there, and I'm about to show you some of them. And that gives you a lot of flexibility because Python can do all of the nice, softer work while it knows that the small boards with microprocessors that are really well designed for real-time work can be off doing that part of it. Separation of responsibilities, it's good design. If you do want to run Python on the control board, as I said, things are better, faster, cheaper, and there are boards like ARM boards and that which are really nice and small, and that gives you a lot of flexibility as well. So I think I've already rehashed this slide. Push it down into hardware where you can. If you have to, C, C++ modules, and use the Python for defining everything up top. It's typically the things like how your system's going to behave that is going to be changing as the scientists or engineers work with it, not the really low level, how do I turn a valve on or off? That's usually pretty straightforward. And then all the other things that you don't want to be writing in assembler or C, data management, networking, user interfaces. So a few examples, and let's see. There's going to be some live demos, and there is going to be tragedy, I'm sure. We'll see how we go. So first off, this is a lab jack. It's a block of plastic with screw terminals, and hopefully you get a feel for the sort of size and that. You can see, oh, that's reversed. You get the idea. These are sensational for just hooking up real-world electronics where you just want a simple, robust interface. There are Python libraries for it, there are libraries for a range of other languages, and the thing just works. I've used this for a car engine management system where it was out in the filth, the dirt, the rain, everything, and the thing just works. It's very nice. There are also boards like your Arduino boards. If you're a hobbyist at all, you've probably heard of these. I'll talk about, there we go, that again in a few minutes. But there's a range of boards like that out there. For motor control, which is one of the really difficult things to try and do in real time in Python, there's a number of really nice boards that you can just push that down and say, your responsibility, just go do it. And if you go browsing any of the typical vendors, SparkFun, for example, in the States, DigiKey, which is a massive electronics vendor in the States, Little Bird, who's here in Sydney, they have lots and lots of boards, lots of cool gadgets, and I'm not responsible for what happens to your credit card. That's right. Once you've actually got a board, how do you talk to it? One of the best ways is, if it has a USB interface, USB to serial converter, and then just use Pi serial. The advantages of it is it just works. It works on a Mac, it works on Linux, it works on your Unix boxes, works on Windows. If you've got a POSIX compliant operating system, it will work, and it will work on Windows as well. Both 2 and 3 are supported, and it's not just a tool for C Python. So if you're actually delivering something like a .NET solution, it'll work there as well. Really well documented, very widely used, so it's well supported. And it's also easy to extend. So if you want to do something odd like an odd RS485 protocol sitting on the top, it's very easy to extend it. You know, your COM port has some sort of a name like that. You just whack that into the constructor as you build it and you'll start talking. But then there's a whole range of other options if you do have an odd configuration. The one catch that I was going to mention was, as you start plugging more and more USB devices in, some operating systems, hello Windows, chokes really badly. So you may find you plug a couple of USB devices in and they come up as COM1 and COM2. Unplug them, plug them back in, and they come up as, say, COM3 and COM5. Yes, love that. Linux is really good because you can code your way around that with UDEV rules. That's just a trap for young players. There's lots of boxes to interface into the real world. First demo, let's see how badly I can screw this up. So this is a weatherboard from SparkFun. So we're talking, what, 2 inches by 2 inches? And on that you get barometric pressure, calibrated already, relative humidity, calibrated. You get temperature, and you can select whether it outputs in Celsius or Fahrenheit. You get ambient light. You get some nice little I/O points so that you can add additional I/O on if you want. You know, there's no cloud sensor or fog sensor, which is what you need in Melbourne at the moment. Now let's see how we go. So I'm on a Mac, as you may have gathered, and this is the name of the serial port that it's given me. No COM1 here. I just want to make sure it's come up correctly. So I'm just going to bring up a serial program for this. CoolTerm's a really nice little Mac program if you are playing around with things like that, and it looks like it's found the right port for me. If we now connect, all it does is every second it just pumps out a line of ASCII. And if you run along, it's actually values like the ambient light, the temperature, which looks like it's in Fahrenheit possibly. Let's not bother. But you get the idea. That's really easy to parse out. It's nicely terminated, and you can actually configure the board so that it will output in human readable format, so it's all nicely tabulated with text, or machine readable, which is that output. So Pi serial, read in the line, parse out the fields, and you're done. It's that simple. I'll show you another board with some real Pi serial code in a second, but hopefully that gives you a feel for just how easy it is to pull out a vast amount of data. If you were going to write your own weather station for home, for example, you could just get one of these boards, drop it in something like just a small plastic box that is optically clear so you still get your ambient light, stick it outside, USB cable inside, maybe 10 lines of Python, if that, and you've got a fully working weather station. That's not bad. The Bitwhacker. So the Bitwhacker is this tiny little board here, and I'll jump back to photo booth for this. It is tiny. Can you see that? So we're talking about just three maybe 3 centimetres long, 2 centimetres high. It is really tiny. It has, though, 16 lines of digital I/O. You can drive motors with it. You can pump out frequencies. You can read voltages. If you want to get started with playing with Python in the real world, this is probably the way to go. The built-in firmware would do anything that the novice would want to do. If you're just getting started, it will keep you happy. But it's easily reprogrammed with standard PIC programming tools. And the nice thing is you can buy these for $25 in volumes of 1 from SparkFun. But you can easily build up your own. If you've got a soldering iron and a PIC programmer, then you can just make up your own, and there's plenty of examples on the web of how to do that. Now, will this stay? Oh, go away. Let's see how we go. This is going to be messy. So I've just wired a little servo motor to the front, and I've got a red LED there. Maybe I need a volunteer. Mark, do you want to hold that for me? Okay. I'm very conscious of some of the live demos I've seen this weekend and how tragically awry they can go. Let's see how we go. So I've written a little script over the top of PySerial. It's just called PyWhacker that just lets me play with... oh, that's what I forgot to do. Okay, so different USB modem port this time. And all I'm going to do is just give it that, and I should have a port. And I should be able to do things like query its version to just see what firmware it's got. And then let's just set up some default port mappings. And what I'm going to do is just drive the LED at a frequency. The LED is on the I/O channel A0, and let's say, is that blinking? Hopefully people can see that. And then there's the servo, which is on, if you were lucky you heard that move. And so here I'm just driving it between home and end, but I can also do things like actually say, whoa, pick a value, tell it I want to go to value 2000. It's that simple to drive a motor. So you've got multiple servo channels. So if you wanted to build your own little helicopter that was Python driven, it might be tethered. I know you could use a Zigbee interface. You could do all that straight out of the box. It's that simple. Thank you, Mark. The really neat part about that is Python is just so easy to network. So think of what you can do with that. Hook it into a Twitter account and get it to monitor your IMAP or your POP account. Wire in 3 LEDs so that every time someone tweets you, the green LED blinks. Every time someone emails you, the yellow LED blinks. Every time your boss emails you, the red LED really blinks. And have the servo hooked up to just a little dial so that it goes between 0 and 180 degrees, and it can be monitoring your server load or the amount of RAM you've got left or your latency for playing World of Warcraft or some other really vital statistic. It's that easy. It's really nice. And that's the board, if you couldn't see it from down far below. It's got a couple of LEDs on it, a couple of buttons on it, and you can solder away to your heart's content or just wire it into a breadboard. And the little trivial interface that I put over it is available there at Bitbucket. But if we go to text editor, and it's not quite maximised anymore, is it? All I've done, like it's not rocket science, I just want to show you how easy it is. So the constructor at the top, it just creates the I/O map, saves the address, saves the port object, and stores the version. And to send, you're just writing a packet out the port. And if you have a look down the bottom at that send receive function, it sends, and then it reads, and it strips off the last character for the response. Further down, I do a little bit more manipulation, but that's it. It is very, very straightforward programming. And this is just a convenience, sort of, an object-oriented layer on top of it. If you want to move up a level, the Arduinos have stacks more I/O, and they have lots of nice little interface boards like this that sit on top. So this one's 4 relays. If you wanted to do things like turn on the pool pump, for example, or you want to switch lights on and off, you could have an Arduino coupled into one of these boards that just plugs in on top and do the appropriate safe, responsible mains wiring, and you'd be away. There are dozens of different shields, which are the shields of the expansion boards that sit on top. So you can have LCDs, wireless interfaces, all sorts of I/O, GPSs, and there's a massive community of people working in this. $35 for a board like that gives you more I/O than the average person would know what to do with. They come in a range of sizes. So you get an idea with the Arduino Mini there and the Arduino Uno. And there are a range of others, including ones that are designed for wearable computing. So you can actually stitch them into your clothing and then use conductive cotton to weave wires out to various sensors. And that's where it gets to be a lot of fun. And the IDE is a really simple variant of C, and you can write just a nice little serial comms handler to talk back to your Python interface and do all of the Arduino magic. So instead of having Python on the computer talking to boards, there's a couple of other options. I mentioned Pymite, and I'm just going to flick over it really quickly. This is a work in progress that is amazing. 8-bit microprocessors with 64K of flash and at least 4K of RAM can run a subset of Python. You don't get the standard libraries, so it's kind of really, batteries are not included, but it does allow you to use Python in a very embedded environment. Where I think Python probably shines, though, are boards like this. This is a Beagleboard. So it's just a standard ARM Cortex A8 CPU. There are a range of operating systems that work on ARMs with Python. So, for example, Debian and Ubuntu Linux will happily run on a board like this. Just load up Debian or Ubuntu onto an SD card, plug it in there, power it up. It's got HDMI interfaces, it's got USB, JTAG, I2C, the works. A little board like that embedded away in a product is exceptionally powerful. It's more powerful than the computers that most of us were using, say, 5 years ago. It's very impressive. And a lot of small netbooks and computers like that are based on these sorts of boards. That's the picture for those of you who couldn't see it from the back. And there's a stack of others. So I showed you this one. This is a Gumstick. This is a fully operational Linux ARM computer. It's got really small little headers. For those down the back who can't see. So that's the size of it, with this tiny little header that breaks out to Bluetooth boards and LCD boards and analog I/O boards. That's how small they get, and this will happily run Python again. Hopefully by now your mind's ticking over going, ooh, I can conquer the world with this. And Raspberry Pi is perhaps the most exciting thing on this screen. For those of you who don't follow Slashdot, etc., a guy in the UK went, I can build a computer for education for $25. And he's now, I think, at the alpha stage. He's got funding. And the aim is to get back to the old days of like the BBC Micro and that, when kids in schools could actually play with a real computer and program it and understand how it all went together. $25 for an ARM-based computer that will happily run Ubuntu or Debian is pretty impressive. I think it is, yes. I think that's the guy. Yeah. I've quickly flicked over PySerial. There are others. Pi Parallel, Pi Visa. Visas are standard used in a lot of engineering boards. And Comedy has kind of died off a bit, but it still works for more high-end commercial data acquisition boards. You may want to know more. It's possible that you have not become an electronics or embedded programming expert just from these slides. I accept that. It's okay. 3 books, possibly all from O'Reilly, but let's move on. I'm not a salesman. I don't get a commission. The Arduino cookbook is brilliant, and the other one is John Oxer, who's a Melbourne guy, has written a book called Practical Arduino, which is also brilliant. Make Electronics is perhaps one of the better entry-level textbooks on electronics. Really practical, great hands-on. And Real-World Instrumentation with Python isn't bad either. That's a book that came out earlier this year. If you want help, inspiration, go find your local hackerspace. Most of the capital cities around the world have them now. And if your city or town doesn't have one, then perhaps you're the person to start it. And I salute you. Let's move on. Threads. I want to talk about a couple of problems with programming Python. Concurrent control of embedded hardware. You have great power and you also have great responsibility because it is very easy to screw things up. First thing is, where do you start? You have so many options. Threads in Python or down in the C level, multiple processors. If you go that way, you're going to use something like the multiprocessing module. Are you going to spawn things out yourself? You're going to work off a single core, multiple cores. How are you going to manage that? Are you actually going to have multiple CPUs and communicate between them? You're going to go fancy with coroutines, greenlets, threadlets, the many, many choices. And the unfortunate thing of having many, many choices is there is no one right answer I can point you at. You do actually have to go and have a look at your design. If you're in a team working with electronics engineers, look at the hardware, understand the trade-offs, and then make the appropriate call. Threads always seems like the easy solution, and to quote JWZ on regular expressions, if you think it's the solution to your problem, you probably now have 2 problems. Because unless you're very careful with your design and understand how your operating system works with threads, you can get yourself into a real mess. And yeah, it just expects sleepless nights if you've got a very highly threaded model and you are controlling a large number of devices with a large number of threads that you're spawning off at possibly non-deterministic intervals. If you do not design it up front well, you are in for pain. This is the gill monster. It's a lizard. It's one of 2 lizards that is venomous in the southwest of North America. So if you're in places like the north of Mexico or Arizona, you may come across this beast. It eats rotten fruit and it eats lolcats. It's not to be confused with the gill, which is also a monster. The gill is the global interpreter lock, and specifically in the CPython implementation, if you are not careful and you try and push your threading too far, you can get yourself into real trouble. I've got a colleague in the audience and he can attest to some of the problems we've had recently trying to debug a system where the threads have just caused us a large amount of heartache. And perhaps the most important thing to remember is throwing more cores at the problem will not solve it, because Python is just working on one core and is just creating its threads on that one core. Again, design up front, think about it. Lower level threads, yeah, may the force be with you. It's often a really elegant solution, but if you're going to try and mix having some threads up in your Python level and some threads down, yeah, Panadol, it works well. Onboard processors, I'm going to flick over. If you're going to do that, just think really carefully about how you manage the communication and sharing between your different processors. The multiprocessing module, from what I've used so far, seems to be a really elegant way of working with it. And as I said, go off board. For example, just have a single thread in your Python application that dispatches events out down to hardware. It's the simplest way to go if you've got control over your hardware. Second problem, what do you do when Python's not fast enough? Probably the approach that I prefer is just to squeeze every ounce I can out of the Python. When I know I can't go any further, drop down into C or C++ and use Swig. There's a range of other tools. You may choose another tool for a particular reason. The thing I like about Swig is it's been around a long time. People understand it. There's good support. Works across a range of compilers and operating systems, and it also targets other languages. So, for example, you can write your C++ library, do the Swig wrapper, and target .NET, Java, Ruby, TCL, Python, all from the same interface. That's quite handy if you're working in a large group that's multi-language. Basically, you write your module, write the Swig interface, compile it, and then you can import it. I'm not going to go into too much more detail. This isn't a Swig tutorial, but that little bit of code there is probably the most complex interface I've ever had to write in Swig. Just doing things like mapping some exceptions and how things like vectors of bytes map up into Python. Usually Swig will be able to figure it all out for you if it's a simple module. Another approach is Python Qt, where what we've done is we've had a Qt application and we've actually embedded Python inside that Qt application. So it's working the other way around. And the nice thing is that Python has access to every object that is derived from QObject inside the Qt framework. So you can start extending C++ classes with Python. You can then push that back down into the C++ layer and have lots of fun interoperably between the two. So we used it for an in-house application for rapidly developing testbeds, prototyping, especially for biomedical work. And the C++ did all of the low-level hardware control and also the UI, just because it was easy to do in Qt. And it worked across platforms, both Windows and Linux, and across different hardware. And Python was the scripting interface and basically was the glue on top of the hardware. So you could talk to the UI, you could talk to the hardware, and create really complex workflows to communicate with the user. That gives you a little nutshell. So there's kind of a brains, which is the controller, and the Python interface can talk across all of those layers. And it's just a really simple user interface. There's a Python script, some control buttons, output at the bottom. You can hide the script, so if a scientist is just running a script all the time, hide it so they just see the output and buttons. But the really cool thing about it was all of the devices are scriptable. The API is automatically generated out of Qt. You hand it over to a mechanical or electronics engineer with Learning Python, the book, and say, call me if you have any problems. And it was almost that simple. It was a really nice way of going. There are other options. People have touched on this in other talks. Things like Python and PyPy are ways of squeezing more out of your Python. I'm running out of time. I'm going to go really quickly. The one here I really wanted to emphasize was high-resolution timing. Don't just assume it will just work out of the box. Understand how your operating system uses timers. Time.time is probably the best way to get a time value quickly on a Mac or on a Linux box, whereas time.clock seems to work more reliably on Windows. And it's good to just abstract that so you remember when you shift your code between platforms. Yeah, and now the shocker, embedding debugger. If you start mixing your C and your Python, or you've got Python talking off to different boards and there's a problem somewhere, I don't have a single easy answer for how you do this. Lots of LEDs on your electronics. LEDs are cheap. Having LEDs that can blink when they're in a fault state, really nice. Plan for it and just build your debug hooks in everywhere you can, as long as you don't compromise your performance. And beware the Heisenbug. So the Heisenbug is basically where the bug is there until you try to observe it and then it disappears. You stop observing it, it comes back. It's the best. Usually what happens is you've got some sort of timing issue or a thread contention. You go, oh, I'll just put in a bit of logging. What do you mean it's gone? It can't have. Take the logging out, it comes back. It's worth understanding when people actually report problems like this and you go and debug it and can't find the problem, just be aware that that's usually an indication that it's thread contention or time contention of some form. I've mentioned this. Python's pretty good at abstracting across platforms, be it your operating system or the underlying CPU. but it doesn't always hide you from everything. And it's really useful to know everything that is going to come back to impact your design. So I mentioned times, for example, but things like how threads and processes are scheduled on Windows versus Linux, how your comms latency differs if you're running USB out of Windows, Mac, Linux, FreeBSD. It's worth knowing that. So I've got a few minutes left. I want to talk about the future. If you're starting from scratch and you're wanting to do something like, you know, hook into an Arduino board, or you've bought a commercial PCI bus A to D card, what do you do to actually get that into an application? At the moment, your choices are, if you're a programmer, Python programmer, you roll it yourself. If you're a C++ programmer, you may get out Visual Studio and, you know, start writing something. Or you can buy Labview off the shelf from National Instruments. And there's not a lot of other choices out there. Some have come and gone over the years, but there's never really been a good rapid application development tool for scientists and engineers and other people who want to work with these sorts of products. Labview is really nice in many ways if you've got the money, if you're prepared to accept that it won't work on a lot of the platforms that you need, that it works best with National Instruments hardware, surprisingly, and that it is very graphical. So trying to do a diff between two versions of something that you've drawn can be a challenge. And it doesn't scale well up to complex applications. A little snapshot of Labview. So you've got some dials and buttons and graphs on the front, and then behind are the widgets that actually tie that together. What I think would be really nice is if there was a Python rapid application development tool that was like that, but learnt from tools like Labview, Visual Basic, HyperCard, Python Card, that was easy to use for scientists and engineers, people that aren't programmers, to actually be able to pick up building blocks of boards like this, assemble them together, hook them into NumPy or SciPy, have graphing libraries on top of it, script into the back if they need additional functionality, suck in packages from PyPy, and have it work across platforms and be open source. That's the holy grail, I think. So watch this space, and I may be doing a demo this time next year. And I would really, if people are interested, my details were at the start, watch this space. Thank you.
We've got time for a couple of questions. So.
If you were just wanted to start out and doing some tinkering, what are the coolest sensors and effectors that people should pick up?
Good question. Did everyone hear the question? What are the coolest sensors and effectors to work with? I think servo motors are really good because they're not complex like stepper motors, but you can use them to drive lots of things. And I think that they're so cheap. You can walk into a J car and buy a servo motor. You know, something like this was, it's 3 leads, $10, $12, including the gear bits. So you could wire that up to a propeller, you could wire it up to a gauge, you could wire it up to a little man that waves at you whenever you get a tweet, whatever. I think that those combined with LEDs are probably the best outputs for starting. In terms of inputs, having some switches is always good just for debugging and testing, if nothing else. But I'm a big fan of weather. I think weather's really good. It's practical, people understand it. And actually, I just realised you being from the Bureau of Meteorology can probably probably appreciate that more than others. But I do think weather's one of those things where it's actually it's all low voltage, it's safe, and it's something that you can just tinker with, and you can compare it against what the news was reporting every night, or hop onto the bomb site and say, I'm seeing that it's 26 degrees at the moment out here, they're reporting 26 degrees. Hey, that's pretty cool. Start doing things like wiring in temperature sensors and humidity sensors into your keg as you do your homebrew, and just monitor the temperature of your homebrew, and then start wiring outputs so you can actually switch on a bit of cooling if it gets too hot. And then before you know it, you've got a second kitchen with a fully automated brewery, and you get a lot more friends when that happens.
Anybody else?
Stunned if not, no.
Just a question about the boards that actually run Python on the board. Compared to Arduino, which puts you through a very low-level programming, relatively low-level programming interface, but has extremely low power consumption, how much more of a price would you pay for actually running Python on top of Debian, on top of one of these small computer boards?
Yeah, good question. Well, with Pymite, it will actually run on the top-end Arduino, the Arduino Mega 2560, I think it is, and they're battery-powered. You know, you can happily run those on a 9-volt battery for a long time. I can't remember off the top of my head the power consumption of this, but it's 5 volts, and I think it is under a watt. So, sorry? 2 watts, is it? Okay, thank you. So, you know, run 30 of these and you've got your average light bulb, for example. That's probably the best thing about them is that they are very low power, which is why people use them for portable applications. Yeah, very, very low power.
Okay, I'm sure you can catch up with Graeme during the break. But let's show our appreciation for a very, very interesting talk.
Thanks, everyone.